Speaking of which, I should look at the chat. Yes, thank you, Andy, for also having Dan Isaacson's site for seminars. And then I really think that the AMS should, and I've told the president of the AMS that just like with Mass Signet and Mass Jobs, there should be something fairly universal that maybe they get the folks who've developed those things. Okay, let's start. So let's recall. Sorry, let me zoom out. So let's let me make sure this is working. 6. So far, I'm not seeing the whiteboard come on my screen. Let's. My apologies. That one seems to be working, but the first one doesn't. Oh, there we go. Okay, so let's recall that we have a way to take this cycles in the bar complex. So in fact, ultimately the homology and the classical associative bar complex that tells us about loop spaces and gives us ways to associate numbers to homotopy classes of maps. And basically that was the last lecture. If I have a cycle, then I'll put this in quotes, but to a map F, I can pull back the cycle, weight reduce it, and then evaluate it on the fundamental class. And then there's I think ultimately a zigzag, but if we switch to the Colli, which is a less familiar bar construction with these graphs. Oh, and I want to have some sort of commutative model. So X is like a simplicial set for APL. You could also use de Rham theory. You get the Q valued, and ultimately this is the sort of just change of coefficients. And then the theorem is that this is an isomorphism of Lie coalgebras. And let's go back to sort of my favorite example. Anyways, the simplest example. If X is a wedge of spheres, then the cochains on X, or at least the APL would be in a suitable way, just equivalent to just a vector space. It'll be spanned, just its homology. So let me just, so spanned by generators in degree di minus 1. And then let me move things here. And then you can, with, this is a chain complex, but you say that the differential is 0 and all products are identically 0. In which case, this bar construction is just isomorphic to the bar construction on these cochains is equivalent to just taking the co-Freely coalgebra on the vector space V. I need to desuspend it, sorry. And then suspend the whole thing. So that implies that the homotopy of X with rational coefficients is isomorphic to the suspension of, just shift degrees up one, the Freely algebra on generators in degrees di minus 1. So this is this follows from so this is due to Hilton, really. Follows work of James on suspensions of a loop, and then the Serre's classical homotopy groups of spheres. There's much more to the theorem than just this rational statement, but then what we get as well is some additional geometry for these. So it is a Freely algebra, and you can take the generators are really, we can think of them as just the wedge inclusions. And what this says is that if you take the Whitehead product or the Samuelson product, so let me just take half a minute to say, recall the Samuelson product. If I've got two different maps, Sn wedge cross Sm, I can take the product of these maps to, this is on the homotopy, I'll just be quick and say on the homotopy of the loop space. Then this goes to the product of the loop spaces. Loops, I can take a commutator, and that's a map on loop spaces. But if I've got an identity, then the commutator will be null, and so up to homotopy, this passes to the quotient Sn cross Sm mod Sn wedge Sm, where it is trivial then, which is just Sn plus m. And that's the Samuelson product. And under this product, and there's some geometry due to Whitehead, yes, I do mean bar co-lead to APL, thank you. There's some geometry, but now we get additional geometry because what we're saying is given a map from a sphere. So you can, there's some lovely combinatorics, which is a lot of fun to play with Freely algebras. There's Hall bases and Linden bases and all sorts of fun areas that you can learn about. But now let's suppose that I gave you two maps from a, say, 57 sphere to a wedge of 4 spheres or something like that. And I said, okay, where is this in this Freely algebra? Or if I gave you two maps, are these homotopic? And well, what we're saying is if I have such a map, I can look at, I call these little PIs on the ith wedge factor. I can look at their pre-images. I'll call that big PI. And I look at all of those over as I varies. And then what this formalism says is that we take So we take, well, so we're going to take one of these PIs and we can co-bound it. And we can then intersect, say, maybe I'll just say I1 and I2, and we can co-bound that. And we can intersect, and this gives higher and higher linking, and so forth. And we do that, and we count when this is discrete. This will be discrete. These will sometimes be discrete. Those counts determine F, up to a multiple, adding F to itself some number of times. So what you, but now let's do the following. Let's choose D inverse, and this is happening. These are all, this is all happening in this R N. So choose D inverse by going up. That is in the direction of the unit vector, the last unit vector. Let's call that En. Going up until you're past all of the, you've got a higher last coordinate than all of the P's. And then you co-bound from there. You finish co-bounding up there. Well, if you look at the recipe, if I just take a single one of these, this will then mean that I'm looking at where PI2 is above PI1. And then here I'll have a point PI2 above a point PI1, and I've co-bounded that further, and then I've got something in PI3. So this leads to counting number of times PI1, PI2, etc. in this order up to some, say, PIK are stacked. So it's really just determined by these numbers, and these can happen with repeats. For example, S2, wedge S2, you only have 2 generators, but the Freely algebra on 2 generators grows exponentially. So you have plenty of repeated linking of sort of things with themselves. What you would want to do is actually take maybe some points close to those original points and count that way. These are framed is another way you can put it. So so this gives a very concrete way to tell whether 2 maps are rationally homotopic after multiplying themselves some number of times, adding them to themselves is what I should say, some number of times. But then the other, and you can even imagine this being something that you could implement if you were an applied topologist, going beyond persistent homology to something like persistent homotopy. If you wanted to understand homotopy classes of maps in some setting, this would be a concrete way to do this. But then the remark is, if we recall the homology and cohomology of configuration spaces, and this would be in Rn and some number of points, just say K, this would determine this count, and this is by these tome classes of submanifolds where points in the configuration where xj to xi, the unit vector, points up. And what you have in that case is that these counts also exactly determine the image in homology. If I take a product of these pi L for IL in some set, their product naturally maps to the configuration space because I can take one point on each. Maybe I've moved them around. So this is now a submanifold of configuration of the cardinality of S points in Rn. And again, yes, the PI are the pre-image of a single point on the ith sphere. So this is, again, take a pre-image of a point on the ith wedge factor. These submanifolds, if I take a point on each one, that gives me a configuration. As I go over the whole submanifold, that gives me a submanifold of the configuration space, and I can take the homology class. So that is, what I really should say is that this fundamental class is in the homology of that space. So that's one explanation for this this Lie coalgebraic bar construction, is that one is when you're taking linking, you've actually got the topology of the configuration spaces, which is governing things. Let me give a slightly more just algebraic perspective as well, what these linking invariants are. So so if I take the homotopy, oops, if I take the rational homotopy, then I can map it to the rational homology, and that's really an abelianization. And this ends up being the homotopy of X modulo the commutator subgroup. Let me move up things again. Again, there's some sort of X finite and simply connected in order to apply this. So let's actually recall, let's give the notation that inside of a Lie algebra, the ith commutator subgroup is inductively defined by taking the I minus first and looking at commutators with that, and gamma naught is just the whole thing. And you could then ask, and how would you determine your image in this homology? Well, that's the job of cohomology. So if I want to determine this, I can f goes to pull back some cohomology class and evaluate it on the sphere, and this is how you can understand the Hurewicz image. This is elementary. But if you're in that, but what if you're in the kernel? Well, then I claim that you can look at this gamma 1 of the homotopy modulo gamma 2, And this is all with rational coefficients. I'll drop those just to have to write less. And these are determined by the single linking invariants. And if those vanish, I think most people in this crowd can understand that if you go to the further kernel there, you're looking at the next term of the lower central series, and you've got the twofold, and then eventually the higher linking. So these linking invariants give you a filtration on homotopy, which is exactly dual to the Whitehead product commutator, Samuelson product filtration. So, so you have the geometry of linking measuring the depth of your commutator subgroup. I think, let's see. I'll just, well, let's see. I think I'm going to switch to a clean board. And start talking about connections. There's a lot of them. I mean, we should really start with Hopf himself. I've already explained a bit how that goes. If you look at the proof of the Freudenthal suspension theorem, there's a linking obstruction there. There's a lovely paper of, I think it was George Whitehead, but actually no, I think it was JHC, in the Proceedings of the National Academy of Sciences in 1947, where he develops some of these linking integrals after Hopf using de Rham theory, and this has been cited a lot in the physics literature. It's a fun paper to look at the citations. A lot more about vorticity than other mathematics. Hilton, in the proof of his theorem on decomposing the loop space of a wedge of spheres, certainly developed these, and then along similar lines, axiomatized by Boardman and Steer. And they actually were looking at maps from a suspension of one space into a suspension of another space. We're of course just looking at spheres, which are suspensions, into more general X. So, but they did. If you look deep enough in what they do, you can read off the counts of stacked submanifolds from what they do in their geometric section. It takes a bit, but that idea is in there. But notice it's a simpler case, because here all products vanish essentially at the cochain level. Now there's this is entirely elementary in Hatcher's book, and pretty much any book on algebraic topology that develops the cup product, you'll see that the cup product of in a suspension all vanish. And you need a little bit more here, essentially at the cochain level. And let me sort of sketch that. So if B is a manifold, then its suspension won't be a manifold, but it sort of will be good enough. And if I have two submanifolds, and I'm thinking of them possibly intersecting, well, if this W and V are submanifolds of B, they're also quote unquote submanifolds of the suspension. The codimension goes up 1, that's fine. And I can still, the theorem that will come back towards the very end of these lectures is that cut product corresponds to intersection. And the point is that there's a homotopy you can make fairly canonically. Well, not canonically, but you know, as much as a sort of a infinity choice, a pretty careful choice where W and V are now disjoint. And so that's a way to remember that cut products are 0 on cohomology, and actually also sketch out that much stronger that in a suspension you really could, you can really take them to be identically 0 on a suspension. So using that means that our bar constructions, we have none of that linking with correction. It's just linking in the Boardman-Steer setting. Again, for maps from a sphere is all we do, whereas they do talk about maps from a suspension. So let me then give an application due to Kashorka, and this is sort of is a big motivator of mine. So Kashorka used Boardman-Steer, Hilton, whoever you want to attribute these Hopf invariants. So he's looking at a link map from a product of spheres into Rm. These ideas come back again. He's then going to say, look, you get a map from that product to configurations of k points in Rm. He then, actually, let me redraw all of this because I want to give myself some space. So you've got your map from a product of spheres to configurations of k points in Rm. He then says, suppose you have a Brunian link, which means that if I forget one point, the link falls apart, then this will be a null map. And basic algebraic topology says that this lifts to the fiber. I didn't talk about these fibrations, but they're key in configuration spaces. If I've got a configuration of k points, I can forget 1. The fiber is, well, I've fixed k minus 1 points. So I just have to think about a configuration of the last point, but it's got to avoid k minus 1. So that's going to be an Rm minus k minus 1 points. And that ends up being a homotopy equivalent to a wedge of m minus 1 spheres. So this lift exists. It is, sorry, that lift exists not on everything, but on, if I quotient by the wedge, the fat wedge, and that's of course itself a sphere. And so Kashorka analyzes the homotopy classes of these maps. Could I repeat the name of the link, please? Okay, so if this this link, let's just, I haven't given you the name of the map, but let's just call it L. And then this is, this map is what I would call conf L, looking at the configuration space as a functor on that link map. And then Kashorka does some basic homotopy theory to relate that to the homotopy groups of wedges of spheres. I'm hoping to, the link falls apart when removing a component, and those are, so I'm assuming that this is a Brunian link. So it's a link with k components, and it falls apart, becomes trivial if you remove one of the components. Let's see. Oh, I need to draw this arrow the other way. Sorry, I haven't filled you in on all of the basic homotopy, but Kashorka proves that this map exists when you're Brunian. An example of a Brunian link is in the classical setting. Now these are in higher dimensions. Are the Borromean rings. So it's a special class of links, but this work has definitely motivated a lot of mine, because let me just say, a project, long-standing project for me, take any knot or link and think about the induced map on configuration spaces for any number of points. What invariants can you make of these? And that's been a main motivation for developing these Hopf invariants. Okay. That's all I want to say for now. I might come back to this, but this is definitely a long-standing project of mine and others, and with some fun recent progress in the case of knots. So what I wanted to do next was connect with some of the main approaches to homotopy theory, rational homotopy theory in particular. So it should also be said that, well, Chen, and then this was later worked out in what I'm saying by a student, Decane, who's an algebraic geometer. They use the basic fact that the homotopy of loops rationally sits inside the homology of that loop space. So the Hurevich image is, the Hurevich map is injective. And therefore, the cohomology of the loop space surjects onto the functionals on homotopy of the loop space. But it's, and so you can use, so you use Chen integrals. And you can also recover the geometry we're talking about, but let me say that I've thought about this a few times, and I've only managed to recover this really at the trivial product level, which I know is what I've talked about most. So for example, and instead of Chen integrals, I'm going to think intersection theoretically. So what you have to do is, instead of this map from S3 to S2 wedge S2, you have to take some sort of adjoint and look at the map from S2 to loops on S2 wedge S2. And then you have to think about the geometry. So now we would, so if I have P1 and P2 on the the two different wedge factors, then I can think about the tone classes in the bar construction. And that's where the Chen integrals live, is this associative bar construction. And again, he did Raman theory, but I'm going to just think about ordinary cochains. And what does this do? It takes a loop and it asks, how many times am I going through P1 and then P2? So let's draw the picture that I usually do for the preimages of P1 and P2. So that's just some link over here. But now, because I've played this adjoint game, what I have to do is sort of divide space with one of my coordinates being loop coordinate. So I'm going to use well, if x is to the right and y is away from us and z is up, I'm going to use the y coordinate as the loop coordinate. So, so that's the loop coordinate. And so that means that if I've got a map from the two sphere, I'm going to think of the two sphere as R2, union of point of infinity. So I'm having to decompose my S3 as this two sphere along with the loop coordinate. And it's saying we have to ultimately count the number of times that I map to P1 and then map to P2. And ultimately, that means, so this, count the number of loops which first hit P1 and then hit P2. That's what the bar construction says. We did that in an earlier lecture, briefly, but we discussed that. And so if I'm decomposing space in this way, that means that my loops are just sort of going across, and that happens once. And we see the stacked geometry coming back again. So we see stacked geometry. So there's these manifolds are framed, but and you could use that framing to produce to push them off themselves, which is needed in the free Lie algebra case to when your generators sort of come again. But here here you actually don't need the framing. And again, you in the bar construction, you would really only need that because we're doing transversality. Some of these, if I have P1 and P2, but then P1 again, I really don't want P1. I want a copy of P1 moved off of itself, so to speak. And there is where you would see the framing, actually. So that's a great question. And again, in here, the same thing would happen. The information's all there in the classical associative bar construction. And depending on our bar cocycles, this one I didn't have any repeated PIs, but if I had a repeated PI, I would need the framing essentially, or I would see the framing in measuring how many times. See, this is measuring how many times in this loop coordinate the blue is in front of the red. And I could also measure how many times the blue is in front of itself. And that's where the framing would come in. So it's there, but I haven't brought it to the fore. Excellent question, Nir. Okay. So now let's get to the sort of the big picture, the more standard versions of rational homotopy theory. So Quillen Quillen starts with the in the background, and this is I don't know who this is due first, maybe Magnus or somebody like that. But if you have Lie algebras, and then you there's a and you can take your Lie algebra G and consider the universal enveloping algebra. Or you can take your, if you have an associative bialgebra, so that's what I want to, or I think, let's see, do I want Hopf algebra? Let me go ahead and just say that. I can look at the primitives. And I get a Lie algebra. And what Quillen realized is an example of this would be chains on a loop space. And after Dan Kahn, I think was his thesis advisor, you showed that you really can do this really cleanly if you think simplicity. So that's a perfectly good, you want to think of this as a perfectly good Hopf algebra. And over here, then it was Quillen who realized that you get a Lie model out of this. Now, he actually has a few different adjoints there. But I'm going to be sketchy on that point from his point of view because I want to connect it with our point of view. But let me just say that remarkably, it's not just at the level of algebras. His main insight is that you can see you move. So his key insight is from algebraic calculations, calculating homotopy groups, to the full homotopy theory, his famous homotopical algebra. I won't go into it, but I just, since we're mentioning this work, and this was one of the first places that his insight, he chose to really develop his insight, it's just worth saying that this is this very rich setting that he first developed homotopical algebra. This is going to be then ahistorical in a sense, but after Sullivan, we can now see more directly that, so, you know, if I've got, say, finite simplicial sets, simply connected, and then I rationalize, I won't make that precise because again, that just would take a while. But finite simplicial sets, Sullivan has this wonderful APL functor, and then you go to DGCA, that's differential graded commutative algebras. And this this is, for lack of a better, these are homotopy theories, and this is what's called a Quillen. This generates a Quillen equivalence. But now, if we can we take this E, that's the bar co-Lie functor, and we go to differential graded Lie coalgebras. This also gives an equivalent homotopy theory. So these, I think of these as three different bases for the same homotopy theory, like literally from linear algebra, just different ways that you can make calculations. Well, the left-hand side, not so much. That's where you want to understand. But these two theories here, I can either compute in commutative algebras, and I'll talk about Sullivan in a bit, or I can compute in Lie coalgebras. But what I wanted to say is that this Quillen functor now has some geometric meaning to it. Namely, I'm going from X, well, to its cochains, and we know what those are, but if I want to think about it, I'll think about the tome cochains. But now we have a bar complex that gives me linking of cochains. When I take homology of this complex, it has to do with linking of cochains. So this Quillen functor is actually a very geometric thing rather than a formal linear dual of something that itself started fairly formal. As promised, let me now talk about the Sullivan theory a bit then. And Sullivan realized, and he said to me that he was just trying to understand what Quillen was doing. Sullivan talks about, is really thinking about things like resolutions in the sense of resolving a module by free modules or that kind of thing of a differential graded commutative algebra. That, if you make it as small as possible, that's a Sullivan minimal model. And let me give an example, because I'm not assuming people know this theory, and this would just be an introduction to Sullivan theory. Let's go back to, I think people are going to get tired of wedges of spheres eventually, right? So just, as I said, this is equivalent to just a q of xy. These are both in degree 2, and modulo all products are identically 0. And let's just take a moment to explicitly resolve that. So what do you mean? What do I mean by resolving? Well, what you want to do is you want to take, remember that if you resolve a module, you take the module and you look for something that's going to be an equivalence. So here I have my x and my y, and then it's all products are 0. So eventually, I've got my ground field, of course, and then this is the ring I'm trying to resolve. And so what you might do is, well, let's start with the same name. Instead of a free module, I'm going to look at a free algebra. So over here in degree 4, I've got 3 different products. And they're mapping to 0. I want something which is quasi-isomorphic. So I have to kill these products with classes here. And it gets worse, it seems, because now that I've put in these A, B, and C, I have things like, well, I do have AX. Oh, well, that's good. That kills X cubed, etc. But I also have a little bit of a problem because AY hits X squared Y. This is all by the Leibniz rule, as does XB. So let me put the degrees here. These are in degrees 2, 3, 4. This will be degree 5. This is degree 6. These two map to the same place. That means their difference is going to be a cycle. That wouldn't give me a quasi-isomorphism, so I better throw in some, I don't know, I'll just call it F for lack of imagination at the moment. It's also going to be in degree 4 that maps to their difference. And the key thing is we're in the simply connected setting, and we're assuming actually things are 0 in degree 1. And even when I have to sort of backtrack like this and fix something, a cocycle that occurred in degree 5 by throwing in something degree 4, you can check that eventually you can play this game indefinitely. And this is, again, a Sullivan minimal model for a wedge of 2 spheres. It's minimal, but it's far from small. But let me show you a different way to produce this, informed by causal duality. Namely, so I'm still going to map to x, y. But instead of just calling these A, B, C, I'm going to give them names that you're going to start to recognize. I can have, instead, gamma x is the generator going to x, and gamma y goes to y. And then I do have gamma x squared. And what's going to kill that is something that I'll call gamma x arrow x. And same for gamma x, gamma y gets killed by gamma x arrow y. And gamma y gets killed by gamma y arrow y. And then remember I had this additional cocycle here, which would now be called gamma x times gamma x arrow y minus gamma x arrow x times gamma y. And what's hitting that is gamma x arrow y. And this game that you can play in an ad hoc way, as I did above, with A, B, C, D, etc. You can now the indecomposables are indexed by this this Lie coalgebraic bar construction. This is exceptional. This is a special thing about wedges of spheres, but it gives you the flavor of what's true. And moreover, the differential is governed by, in this resolution, so in resolution, is governed by the cobracket. So in this example here, the cobracket, remember, is remove edges and let the graph fall apart into 2 pieces. So if I remove this first edge, I've got an x and an x arrow y, and that corresponds to the first term here. And if I remove the second edge, I've got x arrow x and y. And so so you get a resolution that way. So Pedro says one can pin down all higher ambiguities by looking at adic chains. So you get a resolution. I think so. And again, this is just, I'm using the Lie coalgebraic bar construction rather than on cochains rather than chains, although I guess you are talking about the commutative algebra. So in any case, this is essentially I think the same story that you're pointing out, but explicitly using this presentation of the Lie coalgebraic bar construction. So so at the end, yeah. So let me put a plug in for causal duality here. It implies that what you might call the derived indecomposables of a commutative algebra are a Lie coalgebra. So, so you've got that that point of view of causal duality in this in the Sullivan model game. What we're also seeing then is, from a geometric viewpoint, you can some of them are geometrically. We have that this Lie coalgebra, of course, is isomorphic to this object we've been talking about, and you can you first evaluate the Hurevich, evaluate homology, and then when products vanish, that's when you have linking. And when threefold products vanish, you have higher linking, etc. So you see, from the point of view of Sullivan theory, that our homotopy functionals are, you get more and more of them the more products that vanish in your space. Great. Let me, so this gives some geometry to the Quillen functor, and also connects well with Sullivan theory. Let me end this chapter if I can. Let me end this chapter with by saying further work that I intend to do is to look at invariance of maps from X to Y. Let me just give you the rough conjecture, and this would be for simply connected space, and this is the rational, of course, that the linking is still all. That is, you pull back cobound, take cup products or intersection, and you evaluate. Let me make a trivial, so I'm not going to make this a precise conjecture, because in fact I haven't actually managed to put a precise conjecture there. I'll say a little bit about how it's almost precise, but let me just point out that this must be local. If you think about X, for example, a wedge of spheres in the domain, they don't care about, I need to pull back of a cochain on one. If it could be co-bounded on that sphere, then that's good enough to define linking on that wedge factor. So what is almost certainly the right approach to first formulating this and then hopefully proving something along these lines? Well, maps in a different formalism that I haven't told you about are the same as solutions of Maurer-Cartan equations, so Maurer-Cartan elements. In the following Lie algebra, I'll take the cochains on my domain and tensor it with a Lie model for my range. And then you've got a gauge equivalence. Let me move up. And then, so where should invariance live? Something like the chains on X tensor this Lie co-model of Y. So here would be your linking depending on cochains of Y, and here would be your homology classes on which to evaluate. And the Maurer-Cartan formalism fits well because the integrals that I've told you with these D inverses have arisen in field theory in work of Cattaneo and Minev on three-manifold invariants. So there's probably ultimately some way in which you can think about, well, I know there is a way you can think about X, Y as a homotopy classes of maps from X to Y as some kind of field theory on X with values in Y. There are examples such, especially if Y is BG. So, so that's probably the right way to look at it, but I haven't gotten the geometry of it. Yes, there are those Maurer-Cartan models are absolutely have been developed by Lazarev and Berglund and people like that. The work would be going from that Maurer-Cartan to this dual where you would have the linking invariance. So let me end there. I also wanted to say something about Pi1, but I think what I'll do is I'll just give a special lecture on Friday and then next Monday move on to the next topic, because I think this is probably about all I want to have on Hopf Invariants. So I'll stop there and I'll take questions, and then I'll stop the live stream and maybe take more questions. So questions in the chat, please. Yeah, so when I say linking is all, I want to somehow span the, so really what you'd want to do is you need to have some filtration. And you probably want to filter, let me write some down here. So you want to think about X, Y, and the rationalization of Y, and you want to think about in Ly we've got the lower central series filtration on Ly. So, and then that gives you some, so that's a, I have a hard time on the fly getting the maps, all the maps in question in the right direction, especially because I'm about to map out. But you can then ask, the first one is, well, X to Y to L naught Y mod L1 Y. This is, if you look at this for any F, what you're really doing, invariants of that are just looking at the effect of F on homology. The question is, when those vanish, so if some of those vanish, and again, it's got to be locally, so maybe I've secretly got a homology class on X, submanifold on X that I'm thinking about. If those vanish, then I want some sort of linking invariance etc., that then sort of in the standard sense, they're derived versions of the first one. The zeroth one is the abelianization invariant that determine F. So it's a little tricky because you don't have, this isn't a group or anything, but if I have two maps, F and G, I can ask, do they agree on abelianization? And if not, then I know that F and G are different. So if they have different values on homology and cohomology, if they do, then the same set of derived linking invariants will be defined, and then I can ask, do those agree or not for F and G, and et cetera, et cetera. And the vague conjecture is that those kinds of invariants that will be defined just through D inverse and cut product and pulling back. And you can do your D inverses using things with configuration spaces or other kinds of manifold models if you want, but those will determine F and G in this way. So inductively, if they agree up to some point, the same set of invariants will be defined at the next stage, and I can ask, do they agree there? And they'll agree if and only if they then agree on this part of the Lie model of Y. So again, it's vague because this is an open thing, but I think it would tie together a lot of nice rational homotopy theory and the mathematical physics approach to rational homotopy, because almost surely what you want to do is use the Maurer-Cartan formalism to get this. And by the way, another little plug, this filtration is basically the Goodwillie tower. And I might at some point talk about a bit of Goodwillie calculus. But so I hope that helps, Pedro, you understand a little bit better. Again, I struggle a bit because I haven't even formulated a precise conjecture here, other than our Hopf invariants should work more broadly. By the way, for the question of whether F is null or not, Felix Viestra answered this in his thesis, and it continues to be true. So I should have said that. So progress. Hopf invariants determine whether F is null. And that's due to of Felix Viestra. He performs he thinks about a cellular filtration, and then any other questions? I think I'll stop the